Thanks. So I'm Victor Albert, and this is a slightly modified version of my QIP tutorial on overviewing quantum error correction that I gave at QIP 2025 at Duke. And there it was a 3-hour situation, but I definitely have a few more slides than that. So since I have, I think, 3 lectures reserved, I think there's plenty of time here for questions. It's really nice to see audience participation because, I'm dusting this off and I might be brushing by some topics and ideas that I won't realize until you ask. So definitely don't be afraid to ask. No question is too simple because I'm really literally trying to simplify things as much as possible. That's all I can really understand anyway. So, don't think there's going to be super complicated stuff. So if you don't get something, do ask. Right, so thanks for this opportunity to record this. This is great. I'm happy for this to be on YouTube. And here we go. So I gave another series of lectures at the Boulder Summer School in 2023. Those were a deep dive into stabilizer codes, qubit stabilizer codes, and qubit subsystem stabilizer codes for the most part. I encourage you to watch those if you want to know some advanced stuff like code switching and gauge fixing and things like that. This tutorial, on the other hand, will deal with more of a broader overview, focusing on not just the theory but also the practical aspects. Maybe I should say not just the practical aspects, but also the general theory of error correction. And both of these are kind of supplemented by the error correction zoo. So when you don't see a link to something, that probably means that you can just find it fairly easily in the zoo. And the Zenodo link for the Boulder Summer School is there, and I'll post the Zenodo link for these lecture notes soon. So there's a sparse set of resources on quantum error correction. Here are some that I think are relevant. In particular, I will do a brief overview of homology because it's pretty indispensable at this point. And I learned a lot from Dan Brown's homology notes and some videos on YouTube by Norman Wildberger, in particular his introduction to homology. There's also been a lot of software tools. I'm not super into software, but I'll just give you this list here in case you are interested. And there's a new, besides the Grossel code tables, there's a new database, QECDB by Simon Burton, which has quite a bit of codes. Some of them may be duplicates. It hasn't been kind of cleaned up, but it's a very nice place for actual codes as opposed to just record holding codes like there are in the Grossel databases. Okay, so all this business goes back to the 1950s to a guy named Shannon. And this stuff, his stuff basically has survived the test of time in any definition. And he formulated in a very abstract and general characterization of transmission of information via various media in various ways, lossy versus non-lossy, etc. And I'll overview this because I think this is a very kind of indispensable framework. So the type of information that the Shannon paradigm is adapted to can be classical or quantum. The paradigm proceeds basically in these 3 steps. You have a sender and a receiver. You encode the information by the sender. The information is transmitted through some pipe or wire that you in general call a channel. And it's decoded by the receiver on the other end in some way. The encoding and the decoding don't have to be perfect, or in fact, the decoding is never perfect in the real world. It's always just good enough. Right now, information is being encoded, transmitted. My voice is being encoded, transmitted through wires and decoded on your end. And hopefully, contingent on my internet connection, it's fine. The channel would be the internet connection. The transmission can be through space, as it would be modeled through in the case of my voice. But it can also be through time in like a quantum memory or a classical memory, like a hard drive. What's up?
No, I just wanted to confirm. Uh, so what is there on the screen? I just see 1, 2, 3. Are you writing more than that?
No, thanks for confirming. Yeah, I'm talking about those 3 points.
Okay, good. Okay, thanks.
Yeah, here's some more stuff.
Okay, got it.
Yeah. So yeah, so the transmission can be in something stationary in space, but just you're waiting for it in time, like a like a memory or a cell phone that's not moving. It's storing data in a hard drive. That also has a small error correcting code. Um, right. So again, I just want to can't stress enough the generality of this paradigm. Moreover, the type of channel is important. The channel can be smaller than the amount of information you're trying to squeeze into it, or it can be larger than the amount of information that you would be redundantly encoding into it. On the left, I give you this kind of like bow tie picture of the case where the channel is smaller. This is something that is called source coding, where information is compressed, potentially in a lossy way, okay? And in some kind of cryptographic code or compression scheme, compression scheme, not cryptographic code. While in the channel coding scheme, you have more than enough space in the channel to store the information, and now the idea is to encode it redundantly in a way so as to protect it from some kind of noise. On channel coding, but I wanted to mention how this kind of paradigm in one fell swoop encompasses many different areas of not just quantum science, but also classical. So in terms of error correction, there's been a long history since the 1950s. Let me engage the audience here. Who knows what that thing is at the bottom left, that telephone looking thing? Anybody? Anybody who was born before the 2000s?
It's a telex machine?
I think it might be. I don't know. Maybe that's another name. It's a telephone modem. So the kind of modems were the first to use some kind of error correcting codes developed by Hamming and Golay. Maybe you've heard these names. Quickly, they became used in hard drives. So I'm going from left to right. Satellite communication. Let me see. Yeah, satellite communication. Broadcast networks. Then those things called compact discs that you also may not be familiar with. Flash drives. Wireless networks. And sorry, the antenna was transmission through like cell towers, etc. And live here is a broadcast symbol where you're broadcasting information to a large set of users at a time. All of these require different error correcting codes. And so there's been a very large industry of classical error correction over the past, I would almost say now 80 years, developing different error correcting codes for these. And this industry is still alive and well, okay? And it's something that
Sorry,
I
I
think
mean,
is, yes.
so sorry, a very dumb question. So what is the, I would imagine the, like, because a hard disk and a CD compact disk, they seem to be very similar in the sense that they're trying to store data on a physical medium. But why is it that one would construct different error correcting codes for each? And not
Um,
really use the same thing? Is it?
Well, yeah, so off the top of my head, I would say the noise is different. A compact disc is closed up in a shell, so there's really not a lot of noise there, so they don't really do a lot there. But a compact disc, you can scratch it around, so they've used things like Reed-Solomon codes for it. Reed-Solomon has been the workhorse of a lot of these. But Golay went to the moon. They used a Golay code for one of these lunar landers, and they do space communication.
Thank
Anyway,
you.
yeah, good question. Yeah, so memories, classical memories don't require too much error correction unless they're kind of out in the open like CDs. Although flash drives also have had a very interesting kind of direction and set of codes for them. I'm not sure why. I'm not really super well versed in that. But things like transmission, cellular communication, and broadcasting, all of those have a lot of different classes of codes because those have actually very different, the codes are designed for very different tasks. Anyway, it's a whole world out there. I know we live in the quantum world, so just getting back to that, when did that kick in? Well, that kicked in with Shor in 1996 when he realized that you can upgrade classical error correction to protect quantum information as opposed to classical information. So namely superpositions of signals as opposed to just signals themselves. And so error correcting codes for quantum communication and quantum storage, quantum memories, have been developed since the late 1990s, and there's been an explosion of it in the literature over time, the past 10 years, especially very recently. It's very hard to keep up now. I want to mention two modern applications on the right here. So what are they? Does anybody know? The two little pictures on the bottom right? Can anybody wager a guess where
What
classical
is
error
a
correction is still
QR
used?
code?
QR
One
code,
name is a QR
Reed-Solomon is
code. Right.
Reed-Solomon is used for QR codes. So still, if you have a QR code, think Reed-Solomon codes. And the downloading thing that is I gave you a hint. The arrow is a hash function. So when you download a file, the browser compares whether the file was correctly downloaded by using a string generating a string from the file that you downloaded and comparing it to a reference string that it downloaded from the website. And that's an error detecting code. So those two we use every day. Okay, so let's focus on now channel coding, whose goal is to preserve messages sent through a noisy transmission channel by encoding the messages in an encoding, or for short, called a code. So if I've reproduced the channel coding picture here, on the left is the sender, on the right is the receiver, and there's different types of channel coding. Once again, one is the kind of cryptographic channel coding, and there the noise channel is what's called adversarial, or what I call adversarial, which is basically an evil eavesdropper who has kind of human-like resources, who can try to access your message. And so your goal is to encode it in a way that the eavesdropper cannot access it. So you use what's called a cryptographic code for that. They did this in the World War II, etc. They still do. Hopefully, my information is also encrypted as I'm speaking to you over the internet. And the difference between error correcting codes and cryptographic codes is basically, I think it's a very fundamental difference, so it's worth pointing out. To me, the way I view it is that the difference is the type of noise. So for a cryptographic channel, you have this kind of like human who's trying to interfere with it. So it can definitely be the interference and the action of the interferer can be very non-local in space or time. While if you're sending information through a channel where there's not some untrusting party, but it's just a dirty wire, then there's some natural imperfections in it. And those imperfections tend to be kind of random, and they respect locality, some defects and whatnot, typically. And so that's called local stochastic noise. And that's the main type of noise that's assumed in your model of the channel for which you design error correcting codes. But again, I wanted to point out that we're basically around the corner from the cryptography community, which is quite potentially interesting to see if there's any parallels. Similarly, if you're encoding a classical message, which is also known as a superposition, you require a quantum error correcting code. I guess I should also put here quantum cryptographic code, but I don't know much about that. And this quantum code is also designed to protect against kind of local random fluctuations in your channel. And the code should be designed such that on the output, after decoding the message, the receiver receives the same superposition that was intended to be sent by the sender. So this plot is out of date. I would actually looking forward to see how it looks as I plot the last few years. But since the late 2010s, there's been a steady growth of papers on quantum error correction. This is because it's becoming a reality. People are claiming to be seeing the light at the end of the tunnel here. There have been some small scale experiments for a while now, for over 10 years, or maybe just about 10 years. Large scale experiments are coming online, especially in the past few years. So it's a very exciting time. Those experiments while mostly proof of principle, have also started to make it more believable that you can actually scale up these things. It's one thing to do an academic proof of principle result that only works once out of 1,000 times you tried it. It's a whole nother thing to build a machine that works every time. It's guaranteed to work on industrial scales. That's what's happening now. People are actively investing and doing and building these types of scaled up machines. Unclear if it's going to work, but it's I'm becoming more optimistic. But going back to the kind of origins of this, is like I mentioned, it was the whole field of error correction was started by Peter Shor, who not only developed the first error correcting code, but also developed a clean way to do to handle that code, all the overhead you need to kind of measure where the information is and decode and recover the information in a way so that even errors in the measurement procedures can be taken care of. That's called fault tolerance. I'll say more on that. Not too soon after, or very soon after, Alexei Kitaev connected quantum error correction to physics by showing that certain phases of quantum matter have intrinsic error correction baked in. You'll probably know this is the reason everybody knows now about the surface code. And this was something that I think got a lot more people interested in quantum error correction, because this was now connected to many different things in physics and concepts in condensed matter, and those still are being fleshed out 20 years now later today. So this is maybe in part why I'm here talking about this, because as a physicist, I'm not super into the digital nitty-gritty of the computer scientists. And Kitaev also developed a lot more things that I'll talk about today, in particular the CSS to homology dictionary relating codes to manifolds and beyond. A lot of other pioneers are listed here, in particular Daniel Gottesman, along with Rob Calderbank, Eric Rains, Peter Shor again, and Neil Sloan, developed the stabilizer code formalism, which is a very convenient way to do error correction. All the overhead's kind of baked in automatically. It's given to you, all the instructions, and I'll talk to you about that, of course. And Manny Nill was also at the forefront, doing more of a general theory of error correction, as well as some specific implementations in linear optics. Okay, so let me give you a bird's eye overview slide of quantum error correction. We're going to go over in the talk that quantum codes must handle bit and phase noise, not just bit flip noise like classical codes. Classical codes only handle one type of noise. Quantum codes, because they're in superposition, require protection against two types of noise. We will see that this means that the code words of a quantum code themselves have to be in superposition. So not only are you saving a superposition or storing a superposition of signals, the thing you're storing it in itself is a superposition. In the qubit world, this means that quantum error correction requires entanglement, because this superposition will be such that the Schmidt rank, etc., is not 1. In the qubit world, when we have a tensor product Hilbert space, where little n is the number of qubits, each qubit can undergo either error or no error. So that's at least 2 to the n different possibilities of error configurations for the qubits. However, because quantum states have now 2 types of errors, then there's really 4 different errors: no error, bit error, phase error, or bit phase error. So there's 4 different combinations of errors for each qubit, so that gives you 4 to the n different possibilities. This combinatorial blowup is a pain. It's not much more of a pain. Well, it's a little bit more of a pain even than the classical case, which is 2 to the n. We'll see that it leads to some important kind of effects that we have to deal with. Now, how does the code work? Well, the Shannon paradigm I showed you is a little bit of a simplification. If you want to store, let's do a quantum memory in time. you have to figure out, check where the memory is often. And so those red boxes, sorry, the green boxes are checking. You have to measure the errors, diagnose the code, and recover the information back to the code space often enough so that any error that you're faced with is something that you can handle. If you let the information sit inside the red box long enough, there will be a large chance of errors happening that you cannot handle, that the error correcting code is not designed to handle, that are not local. And so then that will lead to an uncorrectable logical error that will happen and will corrupt your information without your knowledge. So you're going to have to correct fast enough. And that depends on the rate of noise, of the rate of occurrence of these errors on the channel. And these green boxes that diagnose the information and correct are called are basically implementing what's called syndrome extraction, detecting errors and correcting them. This part, the green part, I drew it as a long rectangle. It requires a lot of overhead. So you can't just encode and let it sit there. You have to constantly check in on this code. And the checking in part requires ancillary resources, both in space, namely the boxes, and for the best effect of being able to figure out what your information is in time as well. So there's a big price to pay. So don't go into this, thinking it's going to be cheap. Moreover, because of all this combinatorial blow-up business, exactly determining the error, exactly determining, how to correct the error that you're given is very hard, as in like complexity theoretic hard, like sharp P hard. So in a device where the information is moving fast, you're on microsecond timescales, this is going to be impossible to decode exactly. So you have to do heuristic and approximate decoding to be able to keep up. This is something people worry about in superconducting circuits, for example. But more generally, this is true on the theory level for quantum codes on qubits. And even in classical coding theory, this is also hard. It's not quite as hard, but it's also hard because there's a similar blow-up. So that problem never went away. It only became a little harder. Right, that's what I said. You have to rely on some kind of approximate heuristic decoders and decode in real time. Now, and on top of all of this, okay, all the gadgets that I mentioned, encoding, detection, logical gates that I even haven't yet drawn, but may themselves contain errors. So the errors are not restricted by nature to the red boxes, okay? They're actually everywhere. So whatever we do, there's going to be errors. And so we have to handle those errors in some way. Now, we can't just correct all those errors, okay? Because in the process of correcting, we're again introducing new errors. So it's not something we can just eliminate like we can in the red channel, like we want to do in the red box. Instead, we have to tolerate these errors. We have to design our gadgets such that whatever error happens, it doesn't blow up as it propagates through the gadget into an error that we cannot correct. Okay, so this is the art of fault tolerance. Designing fault-tolerant gadgets means designing gadgets that work in tandem with the code and do not amplify errors in a way that the code is no longer able to correct them. So this fault tolerance is built on top of error correction. It requires, as far as I can tell from all cases, the existence of an error correcting code underlying the actual ability to correct the errors, and it requires building gadgets on top of that infrastructure, encoded gadgets that do not amplify or propagate errors from small to large. Okay, and I'm saying this is an art because this is very, very difficult, and it has many ingredients in it. So this kind of a summary slide. Do you have any questions about this? Yes, we're good. Okay. All right, so now let's get into our first error correcting code. It's going to be a classical code. We're not encoding superpositions yet. We're taking it easy. And it's going to be in a continuous variable flavor, because honestly, that's the easiest way I think this is going to work. We're going to be on a circle. Okay, so our physical Hilbert space, but in the classical world, this is called an alphabet, is a circle. Points on a circle. We can put our information on a circle. The message we're encoding is heads or tails, 0 or 1. Classical bit worth of information. So I flip a coin. I have heads or tails. I mark 0 or 1, and I want to send it to you. And I want to send it to you by sending it through a channel where the states are on a circle. Okay? What's the best way to do this? Well, classically, basically, you already kind of inferring the best way to do this. I want the information as far as possible from each other so that any noise won't connect it. So I'll put the circle, I'll put a 0 on the North Pole, as you note on the white ball here, and the 1 on the South Pole. On the South Pole here, okay? And let's see what happens. Now, what's the noise? So your typical local stochastic noise on the circle is just a rotation on the circle. That's basically all you can do. That's isometric, meaning it preserves distances. So that's a typical noise assumption of your classical error correcting codes, that you're going to have some noise that just moves you around in the space in a way that preserves distances. Okay, so the noise has implemented some rotation. I don't know what it is yet. It's a rotation by theta. And now we can kind of immediately infer from the geometry here which theta we can handle and which theta we cannot handle. If theta is sufficiently small, the information is basically around the poles. So if I send the North Pole, I'm stay in the North Pole. If I send the South Pole, I stay around the South Pole. And if I just look at, all right, so we decode based on which hemisphere the information is in. If it's in the northern hemisphere, then we assign it to be 0. If it's in the southern, we assign it to be 1. And so basically you can infer which theta you can handle. If theta is less than pi over 2, if it's less than 90 degrees, then the white ball in the northern hemisphere stays in the northern hemisphere. Same for the southern, and we're okay, and we can recover. If theta is bigger than pi over 2, then the white ball, had I stored in the North Pole, it wades into the South Pole, into the south hemisphere, and we will assign that to be the 1 label upon decoding, which will be wrong because we had sent a 0 initially, and that means we had a logical error, and so we will not be able to correct rotations past pi over 2. I hope this is very simple. Don't get scared away if you're a computer scientist by the continuous variable nature. That doesn't matter in this case. The concept is the same in the discrete case. And just to drive that point home, here's an example of a discrete geometry, what's called the Hamming cube of 3 bits, where all the vertices of it are the bits, bit combinations. There's 8 of them. And in that case, you can kind of encode, again, into points that are far away as possible in the geometry of the cube. In this case, you'll encode in these corners, which translates to a repetition code, the all 0 corner and the all 1 corner. And again, there's other geometries that for which this is the case. You can pack information in the Hamming cube on the left, on the circle all the way to the right, but also we can pack information into higher dimensional Hamming cubes, as the second picture here. Do you see my pointer, right?
Yes,
You guys see my, good. And then in other continuous variable space, you can pack information into the reals, which actually was behind Shannon's original formulation of how to study a particular signal, to map it to a point on the reals. And packing in the reals in a nice uniform way basically is done by lattices. So all of this is kind of the same example of the same kind of feature. Classical coding theory is a packing problem. Noise, like I said, acts by shifting you around in this space. On the Hamming cube, it just moves you to neighboring vertices as determined by the geometry of the cube. On the lattice, it's some shift in the directions of the lattice. On the circle, it's a rotation. And so that's kind of your bit flip noise. You assume it's local, meaning these moves are small in the metric defined by your space. And then once basically to determine the error correcting power of a code, you assign a region of error words, which are these things that you did not use for the code, that are closest to a particular code word than they are to any other code words. So in this case, I've highlighted this region here, the Voronoi, and I call this called the Voronoi region of the all zero state. It's the single bit flips here with single ones. In the lattice case, this is called a unit cell. You're probably more familiar with that, but this kind of Voronoi cell or Voronoi tiling is more general, can be done for any space for which there's a metric defined, basically, notion of distance. And classical coding theory is a packing problem. Voronoi cells determine your correctable regions. Okay, on the sphere, it'll be some kind of arc length that I didn't draw here, but you should get the point. So any questions about that? Oh, right, and the code distance is inferred from these Voronoi regions as the minimal distance between two code words. So half the distance would be the kind of the radius, roughly, of this Voronoi region, and the full distance is just the distance, the minimal distance between two white balls in the packing. Okay. All good? So, like I am implying here, there's many different alphabets that are used to encode classical codes. The example we actually covered was this spherical example, where you're encoding a bit of information, little k equals 1, into the circle, where n here equals 1. The Hamming cube is a binary or example of a binary alphabet, z2 to the n, and you're encoding some, often just some k bit strings into n bit string alphabet for binary code. Classical coding theory people are obsessed with finite fields. We'll get into more on that. This is denoted by this letter F, FQ. You're encoding k query digits, query strings, into n query strings. So it's a qubit version of a classical code. That's the predominant one people use in classical coding theory. There's another one, qubits over ZQ, where you have the integers mod Q. That's not the same as a finite field when Q is not prime. So those are two different query extensions. In classical coding theory, the 1 over ZQ is not super heavily used. In quantum coding theory, the 1 over ZQ is heavily used in physics, but the 1 over FQ is actually used in the computer science formulations when they call it qubits. This was something that I noticed very early on, and I think it's a very important distinction because there's fundamental differences between these two qubits that have consequences both for the physics of the underlying phases of matter developed by these and the computer science or coding theoretic parameters of these codes. Some examples of binary and query codes are here. Reed-Solomon in particular has to be query. It's something that's designed over query to begin with. And a lot of algebraic geometry codes, which are more general than Reed-Solomon in that direction, are also query. Reed-Muller was binary initially. Polar, turbo, and LDPC codes can be binary. And then on the continuous variable side, what they call codes on that side in classical physics or classical coding theory are called, they actually call them modulation schemes. I would call those classical continuous variable codes in analogy with the quantum continuous variable codes. And these are your kind of lattices. QAM is a lattice basically, and PSK is your points on a circle that I mentioned. So it's a classical analog of your cat code. Now, so that's classical in a nutshell. What's different about quantum? We are sending a message, heads or tails in classical world. This message is discrete. All the operations on it are discrete. And especially in the case of hard drives, noise is not too big of an issue. In fact, fault tolerance, which is this ability, it's art form of doing operations that can tolerate errors on encoded systems, was not actively studied, is not actively studied in classical coding theory. There's only a handful of papers that study it because simply people didn't need it. The gates worked really well. People learned that right at the beginning and just went with that. It was not the case in our story, unfortunately. In quantum, we're storing superpositions. So now the message of the alphabet, or the message that we're sending, gets upgraded to a cat 0, cat 1 here, and we're storing superpositions between the two. Unfortunately, we have to deal with much more noise, and our operations now, because we're dealing with superpositions, are continuous rotations that change these coefficients, rotate them into one another, or change their relative phase via a continuous action of the unitary group. So in that sense, I would say we're analog, but you know, it's not really truly analog, because the Hilbert space is still finite dimensional, and we have designed many ways to basically realize these kinds of continuous gates in a discrete fashion to arbitrary accuracy. So this is a very intro slide, but I think it's kind of important to lay that out. So to handle
Victor,
quantum
sorry,
error,
I think there's a question in the audience that they've raised their hands.
Hello, can you hear me?
yeah.
Okay. So when you talk about these alphabets, is there a minimal structure? Do you need a field, a group, or like any minimal structure requirement, or you just choose any particular set and define some properties over it?
I missed part of the question, but I think it was about, do you need any properties of the alphabet to get the error correcting code to work? Is that basically right?
Yeah, sort of.
Yeah. Yeah, so the minimal ingredient you need for classical is the notion of distance. Once you have a metric defined on your space, you have a notion of distance, you have things that are far, things that are close, then you can design packings that correct against things that change you to other neighboring things that are close. So once you have a metric, you can define a packing in that metric that is whose minimum distance is some number, and then you can study that. You don't need the alphabet to be a group or a field. It's not necessary. However, it's very natural to pick groups and fields and rings, in particular fields, because of all their nice properties. Okay, they can add, they can multiply, and the distances is naturally kind of defined already, the Hamming distance. Okay, so you don't need it, but it helps a lot. And so people deal with structured alphabets for the most part, instead of just abstract alphabets, with the exception of some very small corners of the theory community. Let me know if you have a follow-up or not. Hello? Okay. Yeah, just interrupt me again if you want. Right.
So,
So
can I?
yes.
I didn't ask the original question, but I just have a quick clarification question, which is that this has to somehow relate to the physics, right? In the sense that something is being sent over a channel, and the noise is going to somehow move things around, and you want the notion of distance on the alphabet to somehow be related to, I guess, small amounts of noise in the channel, right? So where does the physical link come in describing the alphabet?
Right. So binary alphabets are often, like in a hard drive, can be kind of spins, like, you know, kind of things that are also binary in the physical interpretation. In communication, you're sending over electromagnetic signals for the most part, and those are over the reals, basically. Those are defined over the reals. And so what you wind up doing is you actually concatenate. You first encode your k, you know, logical bits into n physical bits in some abstract code. And then you, on top of that, you encode that code into a modulation scheme. So you pack it inside the reals on top of that. And then you send that over the signal. So right. And then you look at the effective channel on the binary code that is induced by the continuous variable scheme. And it, you know, depending on how you have to pick the code in tandem with the continuous variable embedding, so that the channel that the code is designed against is actually the effective channel that's stemming from the continuous variable side. Yeah, you're right. So that's a good question. And that's why kind of finite fields are okay, because like those physically don't really mean anything as far as I know. But you know, they're just points, so you just a big qubit, and so you pack that into some modulation scheme and you forget that you even dealt with finite fields. It doesn't matter. Right, so now in quantum, you upgrade your alphabet to a space of functions on the alphabet. Why? Because a quantum state where the kets are labeled by, let's say, a 0 and a 1 is literally a function on Z2. The coefficients next to the 0 ket and the 1 ket are literally the evaluations of the function at the 0 bit and at the 1 bit, respectively. So wave functions, we should not forget, are actual functions. So you're storing in the space of functions over an alphabet. Okay. So now all the alphabets basically get an L2 little sandwich, or L2, yeah, prefactor in front of them, which is the space of normalizable wave functions over the alphabet, L2 normalizable. You notice the bosonic one has an S. We can talk about that if you ask a question, but basically it just deals with physically reasonable functions on the alphabet. And the alphabets, again, can be upgraded. Any alphabet can be upgraded to quantum. So the binary alphabet gets basically corresponds to qubit codes. The FQ query alphabet corresponds to Galois qubits. ZQ corresponds to modular qubits. I made those names up because I wanted to differentiate between the two. Then the reals correspond to continuous variable or bosonic codes. And an aspect or a particular case of, the spheres and the circle correspond to quantum spherical codes. And then there's more abstract settings which are relevant to, say, condensed matter, where things are a group or even a category. So those are also group-based codes. There are also a few classical group-based codes as well. Okay, so that's the lay of the land here. Let's go to our first quantum code. We're encoding now. So we're sending a superposition of 0 and 1, heads and tails, with some coefficients, C0 and C1. The coefficients are what we are trying to protect. We don't want the environment to know about C0 and C1. So let's just naively stick with our circle and pick the code that we used before. So we'll stick the 0 ket on the North Pole and the 1 ket on the South Pole. Now we are allowed to have superpositions of points on the circle because we're dealing with functions on the space. Formally, this is the L2 of U1 or L2 of T or L2 of S1 of the circle. All right, so we got kets everywhere now. So what happens when we have some noise? Well, same thing as in classical. We have a noise channel that moves us by some angle theta, so both kets are rotated. Okay, so our superposition of the two white balls is now rotated. Okay, and now we get to these red arrows by some theta. And now what we have to do is slightly different, although it's basically doing what we did in classical. We're trying to determine now what the theta was. But if we do it in the old way, we collapse the logical information. We kill our coefficients. The old way was that we measured which hemisphere we're in. Are we in the north or are we in the south? But if we do that, we're going to only get either the white ball or the white ball in the northern hemisphere or white ball in the southern hemisphere. We're not going to preserve the superposition. So what we have to do is actually measure phi, but modulo pi, meaning we're not measuring points on the circle, but to preserve the information, we have to measure lines on the circle. Okay? So we measure pairs of points and their antipodes on the circle so that the logical information, which is encoded in a point and its antipode, is preserved. Okay? So this kind of modular situation is required for us to be able to preserve the logical information. And this is, again, ubiquitous in quantum coding theory. And this theta modulo pi is what is known as a syndrome. It tells you what the error did to the code. It tells you where the code is. Okay, it's effectively doing what we did in classical, but it's doing it in a way that preserves the quantum information. And this was what people didn't think was possible before. And this is one of the key kind of observations of Shor. So if we do that, we figure out where theta is, and then we rotate back, we're done. We go back to the same superposition. And the same thing holds now for which thetas we can correct. If theta was small, we just rotate back and we're back to where we are. If theta was large, that went past the equator, then we would measure this, and we would rotate back like this, which would flip the 0 and the 1, leading to a logical bit flip. So the error correcting properties are the same. And one thing that I want you to take away is that as soon as theta is non-zero, it rotates your points away. And as long as it's not pi, it maps you to a different ray, a different line on the circle, not the same as the one that we use to store the information, but one that's orthogonal to it. Orthogonal in the Hilbert space is Ketz. Each point is orthogonal, not orthogonal in the geometry of the circle. And any error that takes information out of the code space is detectable. This is something that you only need basic quantum mechanics to figure out. If you have two spaces, one subspace here and another subspace here, these subspaces, if they're orthogonal, that means there exists an observable that you can define that has different eigenvalue on this space than the eigenvalue on this space. Say it has 1 on these 2 points, 1, 1, and minus 1, minus 1 on these 2 points. There exists an observable you can define to measure that, and once you measure the observable, you collapse onto either the code space or the error space, and you can detect the error if you collapse to the error space. If you collapse to the code space, it's as if no error happened to begin with. So this is basic quantum mechanics again, but this is the principle behind syndrome extraction. Okay, syndrome extraction is done by cooking up observables that have different eigenvalues on the code space and all the different error spaces that you're interested in characterizing. Now there will be just coarse enough, it's just fine-grained enough to differentiate between the code and the error spaces, but they will have the same eigenvalue on every logical state within the error spaces, so that they don't collapse the actual quantum superposition. And that's the whole nature of the beast. Okay. I hope you appreciate now circles a bit more. There's a lot there, right? So we're not done yet, unfortunately, because as I mentioned before in the summary, coding over quantum information is harder because there's more noise. Why? Because we're storing superpositions. And superpositions can be affected by a different type of noise called phase noise. And phase noise is something that doesn't move you in this configuration space of states. Instead, it induces a potential on the state space, which multiplies each of your vectors by some coefficient that will be different. In this case, I'm drawing something like e to the I phi on the circle of the potential function by this rainbow circle. And at the top, this thing evaluates to plus. The potential evaluated at the north pole is plus. At the south pole, it's minus. And it's different. And we have no way of correcting it at this point because we have the potential has flipped the C1 coefficient, and the information never moved. So it's as if we had no error. We can't use our bit flip protection, and so we have a logical error that's called a logical phase flip because the C1 coefficient has flipped sign. So what do? Well, the key idea is to encode the basis states themselves in a superposition. So use superpositions for each logical basis state. So here I've depicted using this kind of Mercedes-Benz triangle worth of black points, superposing them to use for the logical 0 encoding basis state or code word, and the upside down triangle of white balls for the logical 1. Those will now be our code words, and we're going to encode A generic state will be C0 times those 3 plus C1 times the bottom 3. So it'll have 6 different points in general. And now if we have phase noise, what's going to happen is phase noise is going to induce cube roots of unity on our 3 black balls. So omega is a cube root of unity. And it's going to induce the opposite of those on the white balls. And now, using our basic principle from quantum mechanics, we have to determine if this error is detectable. Well, if this error took your quantum information outside of the code space into an error space, then it's detectable. And the question is, did it do that? Are these new states with the red coefficients orthogonal to the original 2 code words? Anyone?
Yes.
Yes, because of cube root of unity math. When you take the inner products here, all the arrows are orthogonal unless they're the same arrow. And when that happens, you're going to get this equation, 1 plus omega bar. Right. So, and you were able to do this because you had superpositions to take care of the phase coefficients to map you to an orthogonal state. That's orthogonal because of the way superpositions work. We can recover. Well, in this case, not only can we detect the error, but it turns out that we have enough power to correct it as well. And so we can recover against phase errors by using superpositions. Okay, so that's the code. We encode 0 logical, or the 0th code word, into this superposition, the 1 logical into this. Our bit flip protection, I didn't go over this, but it's more or less maintained. It's determined by, again, it's determined effectively by the classical distance between the sets used to define the code. So now, because we're using a larger set of points, we have a slightly smaller bit flip noise region that's correctable. Instead of pi over 2, it's pi over 6. So we lose some bit flip protection by using superpositions, but we gain our protection against phase noise, which we have to worry about because it also occurs. So this kind of trade-off between bit and phase flip noise is universal in all kinds of settings. You can't, there's no free lunch. If you're really good against one, you're going to not be so good against the other. Codes that are designed to protect against a single type, mostly the single type of noise, are called noise biased or asymmetric. And this kind of trade-off you have to work with depending on your physical system. For those of you who know what a unitary T-design is, I'll mention here that T-designs can be defined in other spaces. Designs are those that average out, whose average gives you the same as the average over the entire space of some polynomials up to some degree T. Well, it turns out that this is relevant for the phase noise because if the points that you use to construct the code, namely the black and white balls, form a T-design, then you're automatically protected against the leading Tth order phase errors. Phase errors are kind of ordered by the degree of their corresponding harmonic induced on the space, and T-designs automatically give you that protection. And this is, again, very universal kind of statement. It also is true for qubit codes, but people don't look at them that way. But there are T-designs called orthogonal arrays on Hamming space. Anyway, that's your first quantum code. Please let me know if you have any questions.
Yeah, so just to quickly make sure I'm following. So everything here so far is using 1 qubit to encode 1 qubit, right? We haven't.
We're encoding 1 qubit into a space of functions on a circle, which is an infinite dimensional space.
Okay. Right. Okay, good. So
Yeah.
that was like, okay, important. And the other thing I wanted to check was if you increase the number of, or the root of unity, right? Like you took 3 here. If you took more, that would give you a trade-off, I guess, between how much bit flip and how much phase you can. Is that correct?
Good. Yes. You'll have less and less phase protection because the points will be closer and closer, but then you'll have more and more bit protection because you have more and more space in the superposition space of each code word.
Yes. I see.
Right. And if you're not comfortable with the circle, you can discretize the underlying physical Hilbert space as well. You can think of it as a big pizza with a lot of slices. So you can think of it as a big qubit. You're encoding a qubit in a qubit, roughly. But all of this kind of stuff will work, except theta will now be discrete.
Right. Okay. Thank you.
Thanks. Yeah, thanks. Please keep asking the questions if the students are kind of shy, you know.
Sorry, I had another question.
Yes.
Yeah. So in the classical case, I mean, we've considered the bit flip error, but we could also consider a channel which leaves the 0 alone and sort of flips the 1 to a 0 with a certain probability, like a
Yes.
old-fashioned channel. Now, those sort of things are not allowed here in quantum, or could we also design quantum codes against those sort of errors?
Good. So that's called amplitude damping channel, and it definitely is allowed, and it's very natural because you have excited states decaying to ground states. And this is a channel that's you can also protect against. It's a more difficult channel than the kinds of channels that I'm talking about, that I can construct using errors that I'm talking about. But in quantum, what's great is that if you protect against some handful of errors, like I told you, bit in phase and bit phase, you can protect against arbitrary linear combinations of those errors. And those errors form a basis for all errors. So any error that can be expressible in the basis of errors that you can correct is protected. And so it's possible to do this. I'm not sure if I'll have I should have a slide on this. I do usually, but we'll see.
Thanks.
Important idea. Yeah. All right, man.
Just a follow up. So what makes the amplitude damping channel hard to correct?
Well, it's what's called a non-unital channel. It does not have a non-identity, an identity Krauss operator. So there's certain noise called Pauli noise. I will have a slide on noise, but Pauli channels are channels where the Krauss operators are all Pauli matrices, and there is an identity Pauli matrix there, which is corresponds to no error. And this kind of no error versus error channels that are Pauli are much easier to handle because they're directly aligned with this kind of linear combinations of Pauli's idea that I mentioned. All the correctable Paulis are just the Krauss operators that are low weight. The amplitude damping channel is different. It doesn't have an identity Krauss. And that's because as the time goes forward, the probability of you losing a 1 state and mapping it to a 0 state, as Jai Kumar mentioned, increases. And if that hasn't happened, you need to re-update the estimates of your states of where you are. Because if it hasn't happened, you were probably never in 1 to begin with. You're probably already in 0 to begin with. And this kind of Bayesian update is what's done by this non-identity Krauss operator to keep things positive definite. And this is kind of a pain because that means you always have something happening. You never have no error. And so you always have to do something. And that's, in that sense, it's hard.
Oh, nice. Yeah, thanks.
So getting back to our little, yeah.
Hey, Victor, can I ask something about the T-design stuff? So you mentioned that T-design is sufficient for protecting for some errors, right? But would you know if there's any kind of like converse statement, like if it's not a T-design, then you're restricted to correcting, like a smaller set of errors, or the further away your points are from forming a T-design, then you're more restricted to correcting some errors, which you know.
Yeah, good question. I don't know. I'll answer this to Andrew because I know he knows this. The real condition is diagonal nil Laflamme, and that only deals with the two constellations being equal. It doesn't equate the constellation to the average over the space. So the average over the space is kind of like an end around way.
Mm-hmm.
So you don't need this condition for this condition to satisfy. And often when you have designs like they'll have slightly more protection because they actually have this extra condition also satisfied that you don't get from the design. Yeah.
Right.
That's all I know. Yeah, I don't know anybody who looked into that. Even just saying this general statement is something that maybe people should write down a bit more.
Right. Yeah, no, I'm just wondering, like, kind of like, if you don't have a T, there's like kind of like this statement that one can say. But yeah, thanks.
Yeah, no, we can talk later more offline. That's like a whole project idea.
Okay.
Right, so back to our alphabet soup, our Hilbert space soup. Let's go back to qubits. I know maybe the computer scientists are getting a little bit nervous, right? So the simplest code for qubits is 4 qubits. It's the smallest code on qubits that detects both bit and phase errors. This is not correcting, okay? It's detecting, but it's good enough for our purposes. A code is defined by a basis. So the basis states or code words are here. They're superpositions of 2 computational basis states, which are the states that are labeled by the binary strings over the alphabet. Why are single bit flips detectable? Well, let's look. They're detectable already, as you can kind of see by looking at the Hamming weight, aka the number of ones of the respective computational basis states participating in each superposition. You notice the Hamming weight of the basis states in the 0 logical is 0 and 4. The Hamming weight in the 1 logical is 2. So you have this kind of spacing of 1 between 2 and 0 and 4. And this is why bit flips are detectable. Let's see what happens if you act on these logical states by the first qubit bit flip, which is represented by this Pauli X acting on the first qubit. Well, it's going to flip the first qubit, so the all 0 state becomes 1 0 0 0. This state becomes 0 1 1 1, and then the 1 logical here, you get a 1 in the first entry and the 0 in the first entry of this guy. Let's call those basis states. Let's define those as error states 0x and 1x. I think it's clear that they are orthogonal to the 0L logic and 1L, so this error is detectable. But we're not done because we want to look at all the other bit flips. So for example, if we look at the second qubit bit flip, we're going to see that the second bit flipped here and here. And now if we squint at these states, we actually notice that these are the same basis states that we had in the first qubit error space, but they're in a different order. Now 0 logical went into 1x and 1 logical went into 0x. And this potentially could be a problem. Before describing the problem, we do want to confirm that these are orthogonal to the code space, so this error is detectable. However, now 2 errors map you to the same space, and the question is, are they correctable? Well, the issue is this order that I mentioned. The fact that the order is different after the second bit flip means that both errors are not correctable. Because if the second qubit bit flipped, you have to undo the mismatch, and you have to map 1x to 0L and 0x to 1L. But if you do that, and the first qubit actually bit flipped, you're going to get a logical error. And vice versa, if you map 0x to 0L and 1x to 1L, same thing happens. So equivalently, you could say that flipping qubit 1 is the same as first undergoing a logical bit flip on the code and then flipping qubit 2, which is this equation. X sub L is the logical bit flip. So because they differ up to this logical, you have to pick which one to correct. This implies that they're not both correctable. Why do you have to pick? Because they both go to the same error space. So you can't resolve them because they're already both in the same error space. If they both went to different error spaces, you would be fine. You didn't need to worry about that then. However, now that they both go into the same error space, you do need to worry about this. And in this case, you run into this problem. All right, now what about phase flips? Well, same idea happens here. Let's look at this. If you have the first qubit phase flipped, then now there's no change in the computational basis state labels. Those stay the same, but the Z error will put a -1 anytime there's a 1 in the first slot here, the first coordinate. Are these states orthogonal to the code states? Yes, because a minus superposition and a plus superposition of 2 things are orthogonal. So this error is detectable. So let's denote this error basis states as 0Z and 1Z. And now let's look at other phase flips. The third qubit phase flipping does the following. And here, you have to be careful with your signs. It's fine here, but then here, if you stick a minus sign out front, you actually notice that this phase flip, this is a typo, takes your information to the same 0Z, 1Z error states as the first or second qubit phase flip did. So again, you have two errors taking you to the same error space, and you have to ask the question now, do they induce the same effect? Unfortunately, they do not. In the first case, 0 got mapped to 0Z, 1L to 1Z. In the second case, 0 got mapped to 0Z, but 1L got mapped to minus 1Z. And this minus sign is now the problem. If you undo the minus sign by multiplying with a minus, one state with a minus as you map it back to the code space, you're going to run into trouble here. You're going to get a logical phase flip if the first or second qubit actually phase flipped, and vice versa. So you cannot correct both of these. However, you can detect them. Similar thing happens with bit phase flips Y, which I won't go into, but I'll just take my word for it that in this case, for this code, all single qubit pal errors are detectable, but not correctable. This is a very canonical code because it forms kind of like a special case of very, very many codes. If you go into the zoo, there's a whole bunch of parents this thing has. And I'll list a few because they're kind of following this kind of 0 to 4 pattern that we saw in the Hamming weights of this code that allowed us to detect bit flip errors. Well, okay, first of all, before doing that, I'll mention that these states are, each of these code words, each of these 0 logical and 1 logical are entangled, meaning there exists no basis that allows you to express them as a separable state with respect to the tensor product decomposition of the qubits. And we needed that because we needed to protect from phase errors, and so we needed superpositions. So there you go, entanglement is required for quantum error correction. So variants of this code include this bosonic binomial code, where now I'm encoding not in binary string configuration space, but in just non-negative integer configuration space that's denoting how many excitations I have in a photonic cavity or an optical fiber, which these and the corresponding kets are also known as Fock states. And if you kind of collapse the states of fixed Hamming weight to a Fock state by taking the Fock state with the Hamming weight of the binary state, then you get this code, which is called the binomial code. And this code actually is able to detect a single excitation loss error in the cavity. You can do this for 2-mode Fock states as well. Kind of split the 4 to 2 cases. And again, this kind of like a 0-4-2 kind of flavor here. You're in a in a 2-dimensional integer space now, but it's still kind of very similar. And another extension is now to map, instead of Fock states, you use Dickey states. So this is a state that's a completely permutation symmetric state. It's a state with 4 1s in it, so it's just the 1-1-1 state. But the state D24 is a state of 4 qubits with 2 1s everywhere. Superposition of strings with 2 1s everywhere. But again, you have Dickey states labeled by the number of 1s they have, and the number of 1s, if you pick to be 0, 2, 4 and superpose the 0 and the 4, you get another code that actually is able to detect errors just like the code I mentioned. However, this code is now permutation symmetric because it's completely constructed out of Dickey states. In fact, this code is obtained by projecting the top code into the permutation symmetric subspace, where the 1 logical now gets appended with a whole bunch of other strings with 2 1s in them to form the Dickey state D24. This is a cute code. It's the smallest permutation symmetric code to detect a single error. And this paper that tries to quantify how much entanglement is required for QEC takes this to the extreme and cooks up this code, which is again also able to protect against, I think, detect a single error as far as I remember. And this is an interesting observation that this code actually has vanishing entanglement asymptotically. but that doesn't mean entanglement is not required. It just means that maybe not too much entanglement is also not necessary, or maybe even detrimental. Okay, good. So we've gone to classical, we've gone over some quantum. Now, there's a whole literature of classical coding theory, and we can use that and mine that to upgrade that to quantum, because half the noise is taken care of by the classical code. We already effectively did that in our example of the circle. The code we used, the classical code we used, is this what's called a 1D spherical code, or PSK modulation scheme. It consists of 6 points on the circle. And we partition, so to be able to protect against phase noise, we need superpositions. So we take our classical code and we can partition the classical code into 2 different subsets, and use each subset in superposition for the code word. And we did that by partitioning the set of 6 gray balls into 3 black balls, 3 white balls, superposing the 3 black balls and the 3 white balls respectively to get our spherical code, or just a 3-legged cat code as it's known. You can do the same. So this kind of partitioning trick is all that you need to do to a classical code to protect against phase noise and to inherit the bit flip protection of the classical code. The bit flip protection is inherited because the smallest distance of the classical code words translates to the same distance for the quantum in the bit flip space, in the geometry. And then the phase flip noise is determined by how many code words, how many superpositions you use. Same thing you could do with a lattice. Take a lattice and color the squares black and white according to the chessboard, checkerboard. You get to superpose the black and the white squares, and you get what's called a Gottesman fresco state, or more colloquially maybe a quantum lattice state. Okay. For the 4-qubit code I mentioned, a slightly bigger cousin of it is obtained by taking this packing of the Hamming cube on 4 bits. You notice this has distance 2 because there's at least 2 coordinates you have to flip to map one white ball to the next white ball, gray ball, sorry. If you partition that, that's got, what, 8 balls. You partition that into 4 sets of 2 balls and superimpose them. You get what's called the 422 code. This includes the code that I mentioned above, the 4-qubit code, as a subcode, meaning this covers 2 of the code words that we used above for the 4-qubit code, but it also includes 2 additional code words. The code words that we discussed are the white balls and the black balls, 0000, 1111, 0011, 1100. The blue and the red balls are additional code words that you can squeeze in there without losing the error detecting properties of this code. Okay. The partitioning scheme that takes in a classical code and cuts it up into pieces according to a subcode of that classical code is called the CSS scheme. So it was established early on. But I can think of these other codes also as CSS-like codes because they're also partitioning the space in a similar fashion. Moving slightly away from the CSS paradigm, but still partitioning, you can take a code on a sphere of higher dimension than the circle, and you can use the geometry of the packing, in this case it's a cube, to split it into subsets as well. So in this case, a cube actually splits into 2 tetrahedra. You can Google it for better images, but the vertices of the cube wind up splitting into vertices of 2 tetrahedra, and so you can superpose points in each tetrahedron to get a quantum spherical code. These codes have interesting gates because they are like kind of non-stabilizer now, but the partitioning kind of idea still holds. And more recently, we had a paper that goes even, does an even fancier partitioning scheme based on something called Tverberg's theorem, which takes codes that are defined over simplices, discretized simplices, which are just basically triangles, tetrahedra, higher dimensional versions thereof, that take packings on these spaces and cut them up into some, partition them up, and use those superpositions to construct codes, which wind up being relevant to permutation invariant subspaces and constant excitation Fock spaces. So anyway, just want to give you the flavor that this is kind of a whole thing you can crank you can turn to take a classical code, convert it to a quantum code, and get very good codes this way. Now, let's do more about these CSS codes over qubits. These come with, yes.
Just a quick question. So, is it clear what advantage one gets from these generalizations? Like if you go to spherical things or when you take more complicated things, is it obvious what kind of advantage one obtains from doing that? In terms of, I don't know, the distances or the rate and so on? Or
Yeah. I think distance and rate are open questions. Like we're just starting to figure out like whether there exist asymptotically good codes on these spaces or not, because they're non-stabilizer kind of codes. So that I'll give you the bad news first. These are non-stabilizers. So all of the syndrome extraction information, how to correct and detect errors, is not known for these codes. You have to design these things. So In-Kai Yang, you probably know him from your neck of the woods, right? He studies this quite a bit. So there's been some efforts there, but you have to do this extra work. However, this comes at a benefit. The benefit is that now that they're non-stabilizer codes, they give you potentially more types of gates that you can't do with stabilizer codes that are fault tolerant. And that's been that's to me is like the real strength of these codes. Also, like if you have a platform like this, like a symmetric space, maximally symmetric space, or constant excitation Fock space, you don't a priori know what code to put on the space. And this gives you a recipe to at least even get a code.
I see. I see. Thank you.
Our dive into qubit CSS codes and how they actually have a very deep structure behind them that makes contact with geometry and topology and homology. And we're going to do this with the easiest code possible, the repetition code. So the repetition code, I mentioned there's a set of operators you need to measure to diagnose the errors for the repetition code to figure out whether you're in the code space or the error space. And in the case of the repetition code, that's just the Pauli matrix products, the relative parities between the first and second bit and the second and third bit. And the corresponding operator that you measure for that is ZZI, where Z is the Pauli matrix, and IZZ. Of course, their product forms another one called ZIZ. And the point here is that instead of dealing with those Paulis that are defined in this, 2 to the n dimensional space, you can just deal with their powers, whether or not Z is to the 0th power to the 1 power, and you can take their powers and put them as rows of a matrix. And that gives you the generator matrix of an underlying classical code behind these Z-type checks. Call them checks. They're stabilizer generators, but it's easier to call them checks because they check for which syndrome value you got. Right? So let's put them all in this matrix and define that matrix to be H sub Z for obvious reasons. Similarly, instead of dealing with cats basis states in a 2 to the n dimensional space, we can just use their configuration space label, the binary string that labels them, put that in a vector space over the binary numbers, all 0 vector and all 1 vector. Instead of dealing with a vector space over complex numbers, we just deal with a binary vector space. So now our little generator matrix can act on the vector space that we got from our configuration space of labels. And I did this for the 2 code words of the repetition code, the all 0 state and the all 1 state. Okay, and now we notice that these have +1. These are in the +1 eigenspace of all these checks. They all have relative parity that's even. In the matrix picture, that translates to being in the kernel of HZ, meaning if you act by HZ on these 2 states, on these 2 vectors, you get 0. And you can check for yourself that's the case. So code words, in this case, because there's no other checks, translate to being in the kernel of this generator matrix. So you can embed a classical code and a quantum code like this by just picking a generator matrix of the classical code, looking at its kernel, and that gives you the code words of the classical code in the quantum state space. But again, we're not done because we need superposition, so we need a way to construct them from these classical codes. And we do that by picking a subcode of the code generated by HZ and picking X-type stabilizers for that subcode, mapping that code to the X-type checks. Okay. So in this case, we're going to do something very trivial. We're going to pick the only subcode of this HZ code, which is just the all-1, generated by the all-1 bit string. Call that HX. That translates to XXX, X-type check. And what we do with this check is we take our states that are in the kernel of HZ and we project them into the +1 eigenspace of HX. Alternatively, I can say it as follows. We can take our code words of HZ and we can organize them into orbits of code words that are connected by a triple X operation. Okay. In this case, well, and how is this done? This is done by applying everything in the HX to the code words in superposition. So in this case, everything is just the XX to the 0, XXX to the 1. So 1 plus XXX. We do that for each of the code words. And in this case, we get the same code word out because 0, 0, 0, and 1, 1, 1 are in the same orbit. So in this case, the resulting quantum code has a one-dimensional state space. It's boring. Okay. But I just wanted to demonstrate the recipe as simply as possible. Okay. More generally, you're going to have multiple things in kernel of HZ, more than 2. And more generally, HX will be such that it actually gives you multiple orbits that are disconnected of code words, and the superpositions of these orbits will give you different code words. So what's the general case? Here's the general definition. You have some generator matrix HZ. It defines a code. You have, I want to say, a parity checkmate. Okay, so you have a subcode that's defined by HX. I won't go into the jargon. And in order to be compatible with HZ, you pick HX to be in the kernel. You pick the rows of HX to be the kernel in the kernel of HZ. You don't want to pick it to be the entire kernel because the quotient of the kernel by the image gives you the code space. So what is a quotient? Well, so here we get into group theory. I've been using this already in passively, so don't get nervous. Okay, we're using binary addition here on these matrices. They form a group. Everything forms a group under this addition here. Okay, so HZ generates a group. HX generates a group. And if we have a group, we can do subgroups. Image of HX forms a subgroup of the kernel of HZ. If we can do subgroups, we can do quotients, which means we can partition the kernel of HZ into cosets of image of HX in kernel of HZ. This requires image of HX to be smaller, to be a subgroup, proper subgroup of kernel of HZ. It was not in the left example of the repetition code with the X-type stabilizer. In that case, triple X generated all of the kernel of HZ, so the quotient of kernel of HZ by kernel of HZ gave you one dimension. More generally, you take cosets, coset representatives V. There's just a single element that represents each coset. Those will label your code space. So they're in the side the logical here, V overline or V logical. And each one will be an equal superposition of elements in the coset, which is just the coset representative plus elements of image of HX, the subgroup. That's a coset. That's the definition of a coset. So these coset states form the logical basis for your CSS code. Okay. That's kind of the group theory side of it, but it's very light, and I'll give you a more graphical description now in the next slide. So I've already mentioned the kernel of HZ is generated by the 111 matrix. The image of HX is by definition picked to be the 1, 1, 1 matrix in this example. Both of those generate the Z2 group. So it's the all 0 string and the all 1 string. The all 1 string plus the all 1 string gives you all 0. That's the whole thing. That there's nothing else. In both cases, Z2 mod Z2, Z1. Trivial.
So just
Now,
a housekeeping thing. You have like about 5 minutes or so for the.
Yeah, good.
Yeah,
Just stop me. Yeah, do stop me, or else I'll just keep going.
Okay, cool.
So now, all of that stuff I mentioned, the kind of algebraic manipulations, have a visual take to them, which connects you to something called homology, which I'll try to describe colloquially. Again, I recommend Wildberger's lectures. Let's map things to kind of a visual setting. We're going to think of our 3 qubits. We're going to think of our 3 Z stabilizers as vertices of a triangle. Each stabilizer, each check, remember, is a product of 2 Z's. And so each vertex here can be thought of as touching 2 edges. And so we'll put our qubits on 3 edges of the triangle that connects the 3 vertices. We don't need arrows here in principle, but just stick with the arrows for now. And in this kind of geometric picture, the generator matrix for the Z-type checks can be thought of as what's called a boundary operator that takes some edges, and gives you the vertices that the edges connect. Operationally, what this generator matrix is doing is assigning checks to qubits. But graphically, what you can interpret that as taking an edge and determining which vertices participate in the edge. So you can think of it 2 ways. You can think of the generator matrix as assigning checks to qubits, or you can think of it as denoting which qubit is touched on by which edge. And that depends whether you take its transpose or not. So don't worry about that. It's just coordinating which checks to assign to which qubits. And you can interpret this as taking the boundary. So if you have a check, you can figure out which qubits it acts on by just acting roughly with this boundary operator. And boundaries are obtained very naturally. So if you act with this thing on this edge, then you get these 2 vertices. And I mentioned the other combinations here. So let's just define it to act this way. Now, remember, we're under binary addition. All these vertices are represented as binary vectors. So when we add 2 copies of the same vertex, we get 0. So you see, if you add the 3 equations that I wrote here, then you see that the boundary of this closed loop is 0. So the action of this thing on this triangle on the 3 vertices is 0. Everything cancels out. Geometrically, this means this triangle has no boundary, meaning that it's a loop. More formally, a one-cycle loop that has no boundary. And the code words that we algebraically obtained in the previous slide correspond to those loops that you cannot contract. In this case, the triangle is just defined using the 3 vertices, 3 edges, and it's got a hole in the middle of it. There's no face. So this loop is non-contractible. Can't contract it because there's a hole there. And the presence of this loop corresponds to the Z2 code space of the code. Okay, so that's the geometric interpretation of the repetition code. Now, we did something trivial 2 slides ago. We added this triple X stabilizer. And I'm going to show you homologically what happens when you do that in this geometric picture. Adding X stabilizers corresponds to adding a third another kind of dimension to our little triangle we're building, namely faces. Z stabilizers are vertices, qubits are edges, X stabilizers are faces. So now, when we add this X stabilizer, we fill in, shade in the hole that we had for our triangle. So you might be thinking that you'll see there will not be a code space, but let's crank it out. Now that we have a two-dimensional face, one-dimensional edge, zero-dimensional vertex, we have two ways to get boundaries. We can take boundaries of faces, we can take boundaries of edges. Boundaries of edges are vertices, we already defined those. Boundaries of faces are going to be edges, and we have to define how to get those. We define how to get those using the X-type checks. So at the bottom here, I've written the boundary operator del X, which is just 1, 1, 1. And the boundary of this single face that we have gives you the three vertices of, the three edges, three edges of the triangle. Together, the three structures of 0, 1, and 2 dimensions, vertices, edges, faces, and the corresponding boundaries, the way to obtain edges from faces and vertices from edges, give you what's called a length 2 chain complex. It's constructed using two classical codes, one for each boundary. The classical codes, and as you might infer, a single classical code corresponds to a length 1 chain complex. All right, and now let's geometrically reprove that we have a trivial code when we do this. Remember, our loops correspond to loops that are non-contractible correspond to code words. So remember, we had this one loop, this loop of three edges of the triangle that we had in the previous slide. Now, the question is now, is that loop a boundary of something or is it not? Because if it is, then we can contract it within that something. If it's a boundary of something, then we can just squish it down to 0 within the bulk of whatever it's a boundary of. If it's not a boundary, then it's non-contractible. There's a hole. And so we have a code word. How do we determine if a loop is a boundary? Remember, our loops are already determined by the kernel of del Z. How do we determine if our given loops are boundaries? Well, we see if they can be obtained as boundaries of some face. And we have one face, so let's just look at its boundary. Let's apply del X to the face. What do we get? We get our loop, according to this equation at the top. So the one loop we had turns out to be a boundary. And so we don't have any code words. We have a one-dimensional space. It's trivial. So the quotient of the loops by those loops that are boundaries gives you the code space. And in this case, we don't have a code space.